Yeah, as I said, so in this workshop, all the slides and the material are available, the recording of the video, but also the slides and the potentially the codes. We actually just discussed that now with my colleagues. Some of the codes are submitted in GitHub within the participants, the speakers' presentations, but we also will try to put it all in one document so it's easier to access. And here we are almost at the end of this workshop series, and we are in the risk prediction classification types of method. We had the first presentation from Chris, Janine, and Anna on using more weighted regression scores, then by Ville, which was focused more on the metagenome and other type of exposome data. And today the session is going to be on the multi-omic prediction using machine learning. And the speaker is Augusto Anguita. He's a senior postdoc at ISGlobal. He has a strong experience in multi-omics, in clinical and biochemical data integration, in particular in the field of metabolic syndrome and obesity in children. And he's going to present today, machine learning algorithm. Augusto,
yeah,
the floor is yours.
Well, I'm gonna start sharing my screen. You have to stop yours first. All right.
So before Augusto start, I'm going to share in the chat we need to know what you thought about the workshop to improve, and I will send in the chat a survey. If you can answer it today or by next week, that would be very helpful for us. Thank you.
Thank you very much, Leah. Can you see the screen properly?
Yes. Yes.
And it is in full screen, right?
Yes.
All right. So thank you very much for the introduction. As you said, we are going to talk about prediction, but making predictions with the special tools that comes from the specific field of machine learning that are explainable and interpretable. And we will see why this is important, especially in healthcare and clinical domains. So just would like to start with a little bit of background about the topic. As we all know, in contrast to the traditional medicine motto of one treatment fits all, in precision medicine, we pursue more personalized healthcare, and we can achieve it by analyzing, for example, molecular data. And the main goal of precision medicine is to analyze multiple sources of omic information, so we can identify subgroups of individuals in which we can actually initiate personalized clinical actions that can go across different levels. Can be for personalized risk assessment, prevention, diagnosis, but also treatment and personalized management of disease. And for that, precision medicine is powered, as we said, by multiple sources of molecular data, that is mainly multi-omics, can be epigenomics, can be genomics, it can be microbiome data, metabolomics, and a large, etc. But also external sources of information, can be clinical, but it can be wearable data, ambient sensors data that monitor the whole environment that surrounds us. And as we have seen in our course, in our workshop, the analysis of these multiple sources of information is a challenge itself, due to, in some cases, the high dimensionality of this data, the existence of complex interaction patterns between markers across layers, multicollinearity, heterogeneity, etc. And everything gets worsened given the fact that normally we have low sample size. for that. So we need powerful tools to address this scenario. Unfortunately, we have some in machine learning. Especially during the past decades, we have experienced a notable boost of some machine learning techniques, highlighting the deep learning technologies that have provide us with an unprecedented ability to make extremely accurate predictions. And it's difficult not to think about the possible practical implementation, no? to approach this concept of precision medicine. For example, we can think about taking a predictive model from deep learning or any other type of machine learning and implementing it into what is called a clinical decision support system, which is basically a computerized program, a software that will support the diagnosis, determinations, treatment decisions in healthcare. But are we ready for that? For answering this question, actually, first we need to understand some basic properties of a clinical decision support system, and we will see if we are close to implement machine learning as a CDSS. First, it needs to be trustworthy, of course. This is the basic property, but it also needs to be fair and ethical. A clinical decision support system cannot make distinctions across between social classes or between different populations by any reason, ethnicities, for example. And of course, it needs to be explicable. If the system makes an error, we need to know why and understand what happened in the system. And unfortunately, this kind of explicability is not a property that we find in the most powerful predictive machine learning methods. And there is not a balance between predictive performance and interpretability, giving rise what is known as the black box paradox. These are models that are extremely good in prediction, but we see the input data, we see the output, we see the prediction, like here in this example with this insect, but we don't know anything about the process in between. And these kind of models of black box algorithms is a problem in biomedical research or in healthcare in general, no? Where we are more interested sometimes in understanding the model rather than the predictions itself. No, we might be interested in knowing the exact importance of the predictors or the directionality of associations, especially if we want to generate new knowledge. And this is important when we are analyzing this complex integration of different sources of data. And this was the motivation for the rising of a new research trend known as explainable artificial intelligence, which is a trend that recommends or promotes using machine learning models that are self-explanatory in nature. For understanding, we are talking about interpretability, we are talking about explainability. These concepts are different. And if we refers to explainability, this is more an active characteristic of the system, is any kind of explanation that the model gives us for explaining its internal functioning, its internal mechanism. And on the other hand, interpretability will depend more on the external observer, on the human side, and is the level at which a given model makes sense for a human observer. So it's a passive characteristic. And this means that we can have an explainable model, a model that offers us kind of explanation about its internal functioning, but it cannot be interpretable if the human cannot understand what it's saying. And this is the example that I'm presenting here, 3 different types of explainable models with different types of explanations, but with quite different level of interpretability and transparency. Interpretability and transparency are exchangeable terms. They refer to the same. As we see here, this model is taking these 3 features to predict a particular outcome. And here the type of explanations that we have is in the way of functions that relates the features. And of course, in this model, as humans, it's going to be easier for us to interpret the results, no? Because the explanations are made in the forms of rules that we can read. Like 95% of the positive training samples have this feature that could be blood pressure, for example, above 180. And this is the first rule. It could be one category, and this is the second rule. This is going to be more transparent and more interpretable than this model, but the three of them, they are explainable. And why is so important to have this explainability and interpretability, especially in healthcare? Well, as we said, for practical implementation, if we create these models, we need them to be trustworthy. And professionals are not going to trust in a model that they cannot understand why it's taking those decisions. Also about transferability. In terms of transferability, we mean that we need to know very well which is the mechanism and the boundaries of a model to see if it can be applied to a different scenario or a different situation. And about the fairness, of course, we talk about ethics, and we talk about making no distinctions among the population. And for that, we need to know how the model works to guarantee that is complying with this fairness and ethics criteria. And of course, if we want to generate new knowledge, we will need this kind of explanations. And this is so important that now European Union has created a huge regulation for that. There is a guideline already for creating this kind of AI trustworthy systems for clinical and healthcare applications, but also there is a draft now, a law in progress for regulating of these kind of systems. But sometimes happens that the models cannot be transparent themselves. They cannot be interpretable. So what do we do in those cases? Fortunately, there are some tools called post-hoc explainers that can help us to dissect what is the model doing as an approximation. It's not exactly, because these models are complex, but these kind of explainers that they are built a posteriori, they can help us to have an idea on why the model is taking those decisions. No? Like, for example, here in this decision for establishing that this is an insect, we can see that the model is basically analyzing the number of legs in the organism. SHAP is one type of these explainers. Is kind of values that we can generate once the model is built. So this is important. First, we build the model. This is a black box model. And then we apply this SHAP technology, this post-hoc explainer, to get more interpretability. And what SHAP produces is a matrix with the individual contribution of each feature for the algorithm decision. And the good thing is that we have this contribution for each particular patient or example in our database. So we will have a matrix like this, where we have features on the columns and patients on the rows. And we can get this information, like which is the exact contribution of the feature age for the algorithm decision in this patient, in this individual. So if we transfer this to this graph, we can see, like always, there is a base rate. This is the baseline risk across the huge population, the whole population. And then we see how BMI, for example, contribute with a positive contribution to the risk class, like 0.1. Blood pressure in this individual contribute with another 0.1. And sex, being female here, being a female here, it is a protective factors with a contribution of minus 0.3. And finally, we can see that age, being 65 years old, is the higher risk factor here in this model. For example, it can be about cardiovascular risk prediction. And the final model output for this patient will be the total sum of all features contribution. And this is very interesting because from these values, from this matrix of SHAP values, we can get a lot of explanations about the model. We can get local level explanations, as I said. We can understand which are the specific risk factors for a particular individual, or even for a particular groups or of populations. And we can also identify if the algorithm makes a wrong decision, makes an error. We can understand why it failed. And this is very important. But also we can get global level explanations, like, as I said, feature importance. If we average the contributions of each individual across one feature, we can get for this feature the importance for the whole model. And this can give us an idea of which are most important variables, the directionality of the associations as well. As I said, is important for extracting new knowledge. And this is a very hot topic now, because most of the most powerful machine learning technologies are not interpretable. So we need actually to apply this kind of sharp values and explainers to get this information. And today I'm going to present case study, how to use this kind of technologies or explainers in multi-omics and clinical research. Especially I'm going to present this work led by University of Granada team about how to use genetics information, epigenetics information, and also clinical variables for predicting a future health outcome. In this case, is a health outcomes related to childhood obesity, to metabolic syndrome, which is known as insulin resistance, which is the previous stage to developing diabetes or this kind of glucose homeostasis problems. And for this, we have this population design in which we have a group of children with obesity, the main of them, the majority of them, and we follow them for 3 years. So the challenge here is that we want to guess, we want to predict the final insulin resistant status in 3 years, but using the baseline levels, using the baseline data for genetics, for epigenetics, and for clinical information. And this is a big challenge because we are talking about a 3 years gap. In a 3-year gaps, it can happen many things. Why insulin resistant? Well, as I said, this is like a cornerstone in the background of cardiovascular disease related to childhood obesity. Is like the connection between obesity and other metabolic comorbidities. So it's really important to monitor the children developing this alteration. And also it's important to study it during early life, during puberty, because puberty is actually like the inflection point, is the point where if a child develops insulin resistance, later is very difficult to revert this situation. So we will have a windows of opportunity here in infancy and childhood to make these accurate predictions and start preventive actions and clinical interventions in those children that they have a high risk profile. For that, we will use multiple sources of information. We will try to integrate epigenetic data, but also protein data, other clinical information, and also SNPs data. And we will have this longitudinal design that is mandatory if we want to build a reliable predictive model. We cannot make these kind of assumptions or predictions if we have just a cross-sectional data set. So with this project, we also try to generate more or less a kind of good practices and guidelines if anyone wants to build this kind of clinical decision support systems, integrating multi-omics data and clinical data, because we have to take into account many different steps during this journey of creating the model. And these are important steps in the data pre-processing, like outliers treatment, missing data imputation, how to handle the dimensionality of these data layers. Also importantly is we need to choose carefully the model that we are going to build. Which metrics are we going to inspect to evaluate the model performance, how to fuse the different sources of information, how to validate our results, and finally, we will see how to use these post-hoc explainers for getting these extra explanations and interpretation of our model. So starting with outliers treatment, we think that it's important to pay attention to this step. Sometimes it's overlooked in many studies, and it's especially for some particular machine learning methods, they are highly sensitive to these possible data outliers. So we need extra attention on that. And actually, we need to address the presence of outliers separately and specifically in each data layer. No, each data layer can be very different in nature, like it's not the same outliers in epigenetic data or in some clinical variables that maybe they will need the evaluation by the human expert. But we recommend definitely to pay attention to outliers treatment before the model construction. Also about missing data, we will have missing data. This is something that we cannot avoid if we have multiple sources of information. And for this step, we recommend, again, using specific imputation techniques by omic layer. Especially here, we performed genomic imputation using reference populations as is agreed in the field, but also we needed to impute clinical data. And for that, I know that in many exposome fields is very common to use imputation techniques such as mice that gives us multiple imputed datasets to kind of address uncertainty during the importation. But this could be a problem if we want to build this kind of models later, because these models normally, most of machine learning techniques, they cannot aggregate or they cannot easily aggregate predictions from different databases. So we recommend using imputation models that can generate only a single imputed datasets. Here, for example, in our case, we used the Miss Forest. Here, this is a comparison between Miss Forest and other imputation techniques. And we can see how, according to the missing rate percentage, actually Miss Forest normally has a high influence, a good influence in models performance. And the good thing is, as I said, that we will get a single imputed dataset. So this is another consideration that we need to take into account when building this kind of models. About data dimensionality, as we have seen during all the talks of this workshop, we are starting with data layers with close to 1 million markers, like, for example, epigenome data or genomic data. After imputation, it can be more than 1 million. And we need first to do a pre-filtering, a selection, a marker selection within each layer. First, because of the sample size that we have. No? We don't have enough sample size to model such huge data sets, and we will suffer the course of dimensionality. So we need these pre-selection filters, but also we need to pre-select the markers for ensuring a balanced design. We need more or less the same number of features across data layers. Otherwise, models will be biased to the dominant or the bigger layer at the time of selecting predictors, or it can even get lost. And in our case, we implemented different strategies for this filtering. For example, for genomic information, since we counted on a good and rich literature on previous studies connecting different genetic variants with insulin resistance and diabetes, we could make this filtering based on expert knowledge. Like, basically, we did a literature review, and we could identify a well-defined set of 150 SNPs that are robustly associated in Caucasic populations, which is the same ethnicity as our population, with these kind of phenotypes. And For epigenomic data, on the contrary, we performed a data-driven approach. This was an agnostic search. We interrogated the full list of 800,000 CPGs with a very robust design in our population and in another population, and we identified a robust list of candidates associated with insulin resistance during the early life. The decision, the motivation for doing an agnostic selection here for epigenomic data and not following a literature review like for the genomic data was that at the end, epigenetics is kind of dependent of the environment where we live. And although there were some available studies in the literature with good EWAS and with good epigenetic analysis for insulin resistance, the populations that we found, they were not totally comparable to our population. So we decided to perform this filtering in populations similar to our study. And finally, for clinical data, we did no actually any filter, since it was a reasonable number of features to handle. So in total, we have for this model around 150 SNPs, 260 or 270 CPGs with information about DNA methylation in these CPGs, and 34 clinical variables that include from BMI, clinical information like sex, age, origin, ethnicity, but also some proteins data, inflammatory markers, etc. So for model selection, we have talked a lot about explainability, about following the SHI principles, but it's difficult to define the model that we are going to use a priori, because initially we don't know actually which model is going to work better in the type of data that we have or in the type of problems that we want to predict. So actually we need to stress test multiple models and compare their performance before choosing the final model to interpret. And this is what we did here. We followed, we implemented a selection of models based on this paper here, comparing different type of classifiers. And we selected a final list of 5 different models that are those that I present here. And we tried to follow the SHI principles at the time of model selection. Because we selected, as I said, 5 models. From these 5 models, only one is self-explanatory. That means that only one, if a human reads the output, can totally understand what it's saying. And this is the decision tree, the C4.5. And then the rest of them, they were complex models that cannot be interpreted by a human without using post-hoc explainers. But the good thing is that we can apply in these models the post-hoc explainers to get these extra explanations. And we can see here how is expected, like the decision tree is the most interpretable one, but the one also with a lower accuracy or predictive accuracy or predictive performance. And probably we can expect from neural networks those much deep learning technologies, algorithms, to offer us a higher accuracy for prediction. And in between, we can find the ensembles models that are a combination of multiple decision trees, and also the support vector machines that try to identify complex nonlinear relationships in the variables to predict the outcome. So this was our selection. And this means that we are going to apply all these models in our problems, and we will compare their performance for the task of predicting the future outcome. About validation, I said this is quite important to validate our model before offering this as a tool or as a application for the clinical field. And this is a challenge when we have such a low sample size. But this is what it is. If we want to incorporate multi-omics information, we are going to have low sample sizes. So we need tools and mechanisms to validate in a way our models in these low sample size scenarios. And for that, instead of doing the classical training, test, splitting, we need to go for this kind of k-fold cross-validation strategies. This is basically dividing or splitting our population in 5 or 10 folds if the numbers allows us to do it. And then repeating the training, test procedure as many times as we need. In this case, we did a 5-fold cross-validation, and we repeated the whole process 5 times over the population. So we can be sure actually that the predictive performance metrics that we get, they are representative of the whole population, and we can fight against overfitting in our data. But again, for validation, we have another problem, which is the amount of cases that we have in comparison to the amount of controls. In our case, from the total of 100 kids that we had in our model, when we look at the final output, the final model, the final outcome after 3 years, only 26 of them developed the disease. Only 26 of them develop insulin resistance, and the rest of them, 64, they are healthy. So this is a huge unbalance, and this means that if we build a model without doing any kind of resampling, probably the model is going to be biased to predict the dominant class. As any machine learning model, will learn better those examples that it has more numbers. And we need to address this with oversampling techniques or undersampling techniques before constructing our model. In this case, we have these two classes, like more cases, more examples of the healthy class. We can actually create false or simulated examples of the disease class, of the insulin resistant class, and we will have a balance in the numbers. Of course, for generating these examples, we have to rely on the existing examples that we have in our data, and there are different methods for that. And also, we can do the opposite. We can eliminate some examples from the healthy class, and finally get this balance in numbers between the non-healthy and the healthy class that we want to predict. And this is what we did here. We, again, the same that the model selection. We don't know a priori which is going to be the best undersampling or oversampling strategy. So we test different of them for each of the models, and we will finally decide which is the most accurate for predicting our outcome. And here we tested 4 types of oversampling techniques, which is SMOTE, NC, ADASYN, and ROSE, and 2 undersampling approaches, which is the near miss and the topic. Then we were talking about comparing different strategies, about different models, about different resampling. But how are we going to compare our models? How are we going to measure how good is my model on predicting the outcome? For that, we have plenty of measures. We have plenty of metrics. We have the accuracy, we have sensitivity, we have specificity or area under the curve, AUC. And the answer for that, it's actually depends on the questions that we wanna, or the problem that we wanna address. Like normally in clinical settings, in clinical experiments, it's more dangerous to have false negatives than false positives. This of course will depend on the disease that we are predicting. But if we are here predicting insulin resistance, if we have a false positive, probably this will be a healthy child that will be incorporated into a healthy nutrition and lifestyle intervention. But if we have a false negative, this is a kid that has the disease and will be left behind this intervention. So in this case, we might put more emphasis in detecting false negatives, and this is more about sensitivity, but sometimes it's more a kind of balance or a trade-off between false positive and false negatives. And for this, we recommend also to use the G-mean, which is a kind of geometric mean between sensitivity and specificity, and it will give us a good overview on how good is the model for these two tasks. About data fusion, well, the most obvious approach would be basically combining all the information that we have into the same model. But the reality is that we won't have the better results if we do it sometimes. And not always the more is the better. And all data combinations should be tested for that. And finally, we will see how to use these post-hoc explainers once we have the model and we select the best models among all our approaches. We will find out how to use these post-hoc explainers to extract new knowledge, to define personalized intervention for particular subjects, or even to discover some subgroups in the population. And also it's important to learn from algorithm errors. So this is the general overview of our approach. So we have this longitudinal design. We have around 100 kids followed for 3 years. And we have a final class, the positive class, which is insulin resistant with 26 of them. And another class that we want to predict, that is the non-insulin resistant, that is 64 of them. We have these 3 layers of information: genetic, epigenetic data, and other endogenous factors with clinical information, but also proteins or biochemistry measurements. We perform this quality control that I explained before about preprocessing. We test oversampling, we test undersampling strategies. We implement validation with repeated 5-fold cross-validation. We test different algorithms, and we evaluate those models according to different metrics. And of course, we will compare different kind of data layers combination or fusion here. And finally, once we identify which is the best approach, we will interpret this model, and we will see if there is a room for applying this model in the clinical. So here is the overview of results that we get. Here is what I show is the G-mean, is basically the performance, the predictive performance of each of the models. Here, this is the decision tree, the random forest, the XGBus. This is another ensemble type algorithm, the super vector machine, and this is the neural network. And what we see here is that in different colors are the different type of data combinations. We have here in orange the combination of epigenetic data with endogenous factors. We have here in a blue square, we have the genetic alone. In an orange circle, we have the epigenetic information. In a yellow triangle, the endogenous factors. And what we see is that in most of the algorithms, the data combination of epigenetic information and endogenous factors is the most interesting for making predictions. Normally, we see that genetic information in our case was not helping a lot to making better predictions. So this is the order of data layers from the less interesting one to the most predictive one, genetic, epigenetic, and endogenous factors. And we see that the best combination is actually the combination of epigenetic data and endogenous factor in 3 of the 5 algorithms. So for this combination, we compare the different models, the different algorithms, and we identify and demonstrate with the Friedman ranking statistics that the random forest is the one showing better performance. And these are the metrics that we got for this algorithm for the random forest across the 25 runs of on the test sets. And we have an accuracy of 0.7, a sensitivity of 0.73, a specificity of 0.69, and AUC of 0.71. So we identify that the random forest is the best classifier in our study, and now we want to interpret why it's taking those decisions. So for that, we built another model, but now in the whole population, to get as much information as possible. And we get these metrics. In the whole population, when we apply the whole model, the random forest, we get an accuracy of 0.90 and a sensitivity of 1. That means that we correctly predict all true positive, and we don't have any false negative. But we need to understand the model, as I said. For that, we will use the SHAP that I explained it in the introduction of my talk, and we will try to get local level explanations, but also global level explanations. Starting with the global explanations that we can get, we can draw these very nice graphs, and this is basically representing each of the features here on the left. And here in the x-axis, what we are representing is the SHAP value. So if the SHAP value is on the left, this means that this feature is contributing in a particular individual. Each dot here is an individual from my population, to predicting this example as a non-insulin resistant, to the healthy class. And if the SHAP value is positive, that means that this variable here in that particular individual is moving the prediction of the algorithm to the positive class, to be an insulin resistant. So at the end, for a particular individual, that for this variable can be here, in another variable can be here, it's not actually just the decision of one variable, but as we said, is the sum of all variables or features contribution what will make the final decision for the algorithm to put him or her in the positive class or in the negative class. But what we can see here is that the upper is the variable, higher are its SHAP values, and it will have a higher importance for the whole model prediction. So this is actually a ranking of the importance of each variable. And also here in color, we see the feature value. So we can also identify and interpret the directionality of association. We can see here how for this variable, low values of this variable, here in blue, are moving individuals to be in the dominant class, in the insulin resistant class. And high values of this CPG, of this gene, are moving individuals to be in the negative class. So what we are seeing here is that a hypermethylation of this gene, a higher level, it will be protective for our disease. So we are extracting information about the directionality of each association. And this is very interesting for generating new knowledge. Also, we can generate this kind of graphs, but splitting the population in different subgroups. For example, here we are creating the same plot, but for non-insulin resistant and insulin resistant. But we can also do it, for example, for male and for females. And we can actually identify if the model is taking different mechanisms to do the prediction in males and in females, and thereby, and therefore we can identify if there are some variables that are more important for females than males, and this would be like sexual dimorphism in the association. So this is another type of information that we can extract from this kind of graphs. And we can go, these were global level explanations, but we can go to the local explanations. We can go to the level of each particular patient in my data and see why the model took a particular decision for this patient. For example, here we can get the SHAP values for patient 1. And finally, the final output of the model is 0.6. This is above 0.5. So this means that with this patient, the model will say it will be insulin resistant in the future. But we can see why the model took this decision. We can see that the most dominant or important feature that the model is considering for taking the decision is the methylation of the HDAC4 gene. That this is a very important gene in obesity and diabetes. We can also see that the model is using iron. the ion levels of these kids are pushing him to be in the insulin-resistant class. But also this ratio between leptin and adiponectin, these are proteins, inflammatory proteins, or inflammation-related proteins produced by the adipose tissue. So this is quite good. And finally, is the BMI. So we can see that here is not much about adiposity itself. It's more about the metabolic status of these kids, what is pushing him to be in this insulin-resistant class. And this is very good from the clinical point of view, because we can actually go to this particular example, give this patient a prediction, and start intervention for his particular case. And this is actually what we look for in personalized medicine. No? We could say, let's start an intervention to reduce, to induce the hypermethylation of the AEC4, if any. We could treat the iron deficiency this kid is suffering, and we could also try to fight against the inflammatory status that he may have, probably due to the leptin adiponectin dysregulation. So this is very nice from the clinical point of view. Also, we can generate this kind of plots that will relate the SHAP contribution of this feature with the values of the feature. So we can identify how in 0.8, this variable start to contribute positively to the insulin-resistant class. And we can extract this information for deriving clinical threshold. For example, we can identify or later validate if 0.8 is a good clinical threshold for extracting, for making predictions with this variable, no? Or the same for the methylation of this gene. And finally, we wanted to present novel ways of using the SHAP values for getting even more information on how the model makes predictions. And here what I'm showing is a heat map for all the SHAP values. Here in the rows, we have the patients. In the columns, we have the different features or biomarkers. And in the heat map, we are showing the SHAP values. So a red value will mean that for a particular individual, this feature will contribute to push or to move this individual to the positive class, to the insulin resistant, and a blue or green value, it would be the opposite. This feature is contributing in these individuals to move them to the positive, to the negative class. So we can actually work with these SHAP values, and for example, doing clustering. We can create clusters based on these SHAP values, and we will find group of variables that contribute similarly to the model. That means that they cooperate to take decisions in the model, in particular subgroups of individuals, but we can also get information if there are subgroups of individuals in which we find different risk factors for the disease. And this is what we did here. We identified four groups of variables, one of them integrating endogenous factors and DNA methylation, three of them only with DNA methylation, and then four groups of kids. And this is very interesting because we find here in this group, for example, DNA methylation data and endogenous factors are contributing in the same way, putting these kids into the positive class. But for example, here, we can see how there is a group with BMI pushing them to the positive class. Like here, BMI is more or less red. But this DNA methylation, what is pushing them to the right decision that is in the non-insulin resistant class. Or the opposite, these kids have a profile, DNA methylation profile, more typical of an insulin resistant kid, but is their BMI, low BMI, or low inflammation, what is making the algorithm to take the final decision to push them to the non-insulin resistant class. And this is very nice. Also to understand how it's a total combination of variables and it's not only clinical information what makes the final decision in the model. And finally, we can use this also for learning from errors. And what we did here, it was taking those examples in which the model does a wrong prediction. in those individuals in which prediction failed. This was a group of 9 individuals, which the model predicts as insulin resistant, but they are non-insulin resistant. So these are false positive, for false positive examples. And what we see here is actually that in the prepubertal state, both DNA methylation and BMI, there were values typical of insulin-resistant kids. So this is why the model decided to put them into the insulin-resistant class, because they are exactly the same than insulin-resistant kids. Indeed, if we study what happened in these 9 false positives, this is the BMI. This is the prepubertal BMI, which is the one that we are using to make the prediction. And this is the pubertal BMI. And we see how they drastically decreased their BMI during the intervention. So for some reason, these kids were a very high risk group, but they did something during the 3 years that made them to reduce their metabolic risk, and now they are not in the insulin resistant class anymore, and this is why the model failed. So probably they adopted a healthy lifestyle, and this information, it was not included in the model. So of course the model is taking wrong decision, but with a good reasoning and justification for that. That is also a message of hope, that predictions are not deterministic. So we can make predictions, but with a good intervention or a good plan for fighting against the disease, we can actually make these predictions not to come true. And here are some key home messages from the talk. The first one is that specialist physicians need to understand decision-making mechanisms of clinical decision support systems, especially in healthcare and healthcare areas. That for integrating multi-omics and external data with these predictive purposes, we need actually to pay a lot of attention to the design of a good analytic pipeline, the whole pipeline from data processing, data fusion, model selection, etc. And that during this whole process, transparent models should be prioritized. Like first use transparent model, and if not, using post-hoc explainer that we have seen in our example that can be used in many ways to extract a lot of information from the model. And finally, I want to acknowledge all these people here. This is a team effort, what I presented today, coming from a lot of work from different projects across Spain, part of the Institute of Health Carlos III, University of Granada, and of course, ISGlobal. So thank you very much, and I hope that my talk was explainable and interpretable, and happy to take questions now.
Thank you, Augusto. It was really nice to see you work at the application of this algorithm in clinical studies. So there are some questions. If I go in the order, Tatiana, she asked why in this study you didn't try to combine all the layers, epigenetic, clinical, and transcriptomic to check the performance?
Okay. Yeah, that's a good question. We actually tried. Let me find them here. We tried all these combinations, including all of the layers separately, their combination by pair, but also the combination of the 3 layers. And surprisingly, this was not the winner in terms of prediction. And there might be many reasons for that, like genetic data were included in the model as individual SNPs, and we know that SNPs sometimes need to be aggregated through scores or any other type of information, but this is an example that sometimes is not the combination of all data layers what makes the better prediction. Yeah.
Okay. And then we have a question about reverse causality. Could some of this association be due to reverse causality? Victor says that he's struck by the fact that iron seems to be a risk factor, but also that iron deficiency is often more frequent in children who are overweight due to chronic inflammation.
Yeah.
Maybe iron deficiency is an indicator of inflammation.
Absolutely. This is the perfect example about that we are exposed to this kind of mechanisms like reverse causality. It might happen here. We address it using a longitudinal design. Actually, we are not using any type of health outcome information from the baseline period. We train our model only with predictors at the baseline and health outcome data from the 3 years follow-up. But it's difficult to avoid that some of the kids that are insulin resistant here, they remain insulin resistant. And of course, there will be a correlation between this health status and this health status. And it could happen that some of our associations are actually reverse causality associations. And this is why knowing what the model is doing actually helps us to achieve this causality in the inferences. Yeah.
And then another question, Yagadesh, can we specify a sequence to maintain biological relevance while we build our model rather than using predictors across biologically distinct domains?
Well, I don't know if I understood well the question. A sequence, a biological sequence instead, in terms of what? Like giving more importance to some layers, or if she or
well, here is giving the example of the biological layers of first genetic, epigenetic, clinical markers.
Yeah, I guess that
the hierarchy in the omics layers, no?
Yeah. I think this is a good point. And it's in line on what I said before. Like we can actually try. This is like for future work. There are many ways of combining the information here. The fusion was done only combining the different layers, but actually there are ways with some models to give more importance to some layers if we expect so. And yeah, this is something that we need definitely to explore.
Okay, thank you. And right, and then that's a question maybe more for clinical settings. How do you update the model while working with the clinical system? There is a knowledge base that continue to change over the years.
That's a good point. Yeah, if we like, of course, in this project we are very far from a real clinical application. We wanted more to show like a guideline or a pipeline on how these models need to be built for future clinical application, but with only 100 kids, we are far from that. But it would be ideal that if we have a dynamic database getting more input, we can refine our model, including those new examples. And of course, the model will change. It will get updated, but also the predictive performance, it will improve, and the generalizability of the model will be better. So this is a very good point also to consider for the final application of these technologies.
Okay. And it's 5:30 past, so I would close the session here. Thank you very much, Augusto. It was very well explained. And yes, I remind everyone we have a survey for the course. If you can fill it, there is one more session in a week, and it will be the end of this workshop series.
Thank you very much, Lea. Thank you, everyone.